So let's take a closer look at this idea of an Anova. What we want to do is we want to compare different treatment means or different population means. Our null hypothesis is always going to be that all the means are equal. So mean 1 equals mean 2 equals up to, say, mean k. And then the alternative is going to be that at least two means differ. So the opposite of not all of them are the same is some of them are different. So we're going to accomplish this using Anova, or analysis of variance. So we're analyzing the variation within the groups and between the groups. Here's the requirements for an Anova. We need to have k simple random samples to start with. So that'd be one from each population or one from each treatment. The samples need to be independent of each other. So subjects in one group should not affect or be related to subjects in another group. Populations need to be normally distributed, all your populations. And we're going to assume that the populations all have the same variance, sigma squared. So sigma 1 squared equals sigma 2 squared, etc. Now, if one of those assumptions is not satisfied, then we have to move to nonparametric statistical tests. So the goal of Anova here is we want to determine if these samples come from populations with the same mean, or at least one sample comes from a population with a different mean. So here's the conceptual idea. Let's say that we have 5 people. We're going to give them 3 different types of drink, and we're going to measure the reaction time. So we'll give them water, or we'll give them chocolate milk, give them a shot of sugar, or we'll give them some Red Bull, so sugar and caffeine, see what happens. So our null is going to be that all the means are equal, so that's saying type of drink has no effect on reaction time. And the alternative would be that the means are not equal, so that would be saying that the type of drink does have an effect. So we're going to analyze the variation in the experiment, and the total variation has 2 components. The variation within the groups, so that's variation among individuals, and then the variation between the groups, so the variation that's due to a different drink. So look at these first, so here's our first scenario here. So we've got reaction times that are arranged from smallest to largest so that we can compare for the 3 drinks. And this is the 5 individuals here. And what we see is that the reaction times here have about the same spread or about the same variability within the group, but they don't look like they're different, for the different groups. So there it looks like we've got variation within the groups, but not much variation between the groups. So, from 6 to 12, it doubled, so there's a fair amount of variation within group, 5 to 11, 5 to 11. But, the spread in each group looks approximately the same. So this is saying that the difference in variation is due to the people and not the drink. Now, the other possibility here is that we see our scores here are very close. So 11 to 14, 5 to 7, and 3 to 5. So there's not much variation within the groups, but we do see a lot of variation here between the groups. So these reaction times are in the 11 to 14 range. With chocolate milk, they drop down to 5 to 7, and with the Red Bull, 3 to 5. So in this case, the difference would be due to the drinks and not the people, because there's lots of variation between groups, but not much variation within groups. So this is case A, and this is case B. And then the way that we will measure, that is our test statistic to measure how extreme our sample is we're going to take the between sample variability, okay, the variation from the different drinks, and then divide that by the within sample variability. And so if F is bigger, that means that there's more variation between samples than there is within samples, and that would mean that the differences in reaction time are due to the drink and not due to the people. So a bigger F value is more extreme.